Over the last decade, asset-intensive industries have poured billions into digital transformation. Yet, when a critical alarm fires, the technicians on the ground still lose hours every week simply hunting for basic answers. This breakdown is happening right now inside telecom networks, medical device fleets, energy grids, and the massive data centers powering the AI boom. The first line here represents physical infrastructure complexity, accelerating rapidly. The second line is skilled labor supply. As veteran experts retire, operational knowledge is plummeting. The widening space between them is the execution gap, the void between a digital alert and a physical repair. Trapped in this gap, field teams default to a reactive cycle. They have to hunt through disconnected maintenance management software, ERPs, and outdated PDFs to figure out what went wrong. That friction carries a steep price tag. Every time a ticket requires a preventable field escalation because the right knowledge wasn't available, it costs an organization upwards of $450. As decades of tribal knowledge walk out the door, trying to close this gap by hiring more people or buying another legacy software tool is a mathematical impossibility. Many leaders hope a standard generative AI chatbot can solve this by summarizing PDF manuals for technicians. But standard language models are built for content creation, not for physical environments. They cannot navigate the strict compliance requirements or the actual mechanics of operational physics. Take a standard troubleshooting scenario. Generic AI reads the manual and outputs a linear rule. Fault code detected, replace part X. But an expert knows that in high humidity, the system must be flushed first, otherwise the replaced part will fail again. Deploying basic task automation to read manuals is like building a simple linear canal. It works for straightforward routing, but it breaks down under the demands of critical infrastructure. This diagram illustrates the necessary evolution. In IT operations, systems had to shift from reactive event monitoring to AI operations driven by machine learning anomaly detection to maintain business continuity. Field service requires this leap toward level 4 autonomy. Capturing a retiring expert's judgment requires a purpose-built digital organism powered by physical AI. Building that digital organism starts by confronting the most stubborn bottleneck in field service: unstructured data. Every enterprise sits on massive archives of dark data. These are the thousands of PDF manuals, raw machine logs, and the handwritten notes from technicians buried deep inside legacy systems. The foundational tier of the physical AI architecture is the memory layer, designed specifically to ingest this chaotic information. Instead of forcing engineering teams into massive, multi-year data cleanup projects, the memory layer processes and structures these diverse formats autonomously. This ingestion happens natively. The system plugs directly into an organization's existing systems of record, like SAP, ServiceNow, and Salesforce, leaving the raw data exactly where it is. By conquering dark data first, the organization creates a clean, usable foundation. This allows the AI to move beyond basic keyword search and into actual reasoning. To reason accurately about the physical world, the AI cannot rely on isolated data points. It must map multiple vectors of reality simultaneously. This mapping happens inside the context graph, the central architectural brain of the digital organism, built on 4 distinct pillars.
The first pillar is asset lifecycle context. It tracks the physical history of the machine itself, from installation details and site conditions to predictive failure rates. The second is enterprise context. This integrates the business constraints, pulling in specific customer service level agreements, compliance codes, and supply chain histories. The third is human interaction context. The system recognizes who it is talking to, adapting its technical depth depending on whether it is guiding a novice technician or a level 3 OEM specialist. The fourth is the system of engagement. This is the omni-channel ingestion layer that understands and responds to IoT machine logs, voice commands, and live chat. When an alert fires, the context graph instantly cross-references all 4 pillars. This gives the inference engine the situational awareness required to predict root causes and orchestrate fixes based on the actual physics of the operation. To see how this architecture translates into operational reality, we can look at critical telecom infrastructure deployments, like those at Nokia. They utilize an L4 system of agents. Rather than one massive AI trying to do everything, 16 specialized agents execute distinct functions, coordinating autonomously like a fleet. It begins with the detective. This agent scours incoming machine logs and service histories, extracting anomaly signals from the noise without requiring any human intervention. That signal passes to the diagnostician. By correlating the anomaly against millions of historical data points in the context graph, this agent pinpoints the exact root cause of the hardware failure. Next is the strategist. It takes that root cause and cross-references it against a massive global supply chain, optimizing thousands of unique spare parts across hundreds of depots to locate the exact replacement needed. Finally, the planner maps the availability of that specific part to the correct technician's schedule. It compiles a complete game plan and sends it to a mobile device, ensuring the tech has everything they need before a truck ever rolls. Out of the box, this multi-agent orchestration automates over 1,800 complex workflows. It ensures the right solutions are in place before failures strike. But the physical world still has hard constraints. An AI agent cannot turn a wrench, reroute a high-voltage cable,